In the previous class, we have observed how a signal can be decomposed in the even part and the odd part. We had taken an example of a continuous time signal. In this video lecture, let's look at decomposing a discrete time signal. As far as the formula for decomposing the signal in even and odd component is concerned, it is the same. Let us consider a signal of say x of n, which is say 2, 1, minus 1, 3 and 2. So this is having 5 samples in it. Let us look at the way in which we can decompose this in even and odd part. Observe that the even part x even of n is given as half into x of n plus x of minus n, x of minus n. This is the formula. As far as x of n is concerned, it's already given. X of minus n is nothing but the time reversed version of the same. So to obtain the time reversed version, we will just fold the signal along the origin. Origin over here has been marked at minus 1, right? So you can think of these samples as minus 2, this is minus 1, this is 0th sample, this is first and this is the second sample, right? So these are the index. So indices of the signal are minus 2, minus 1, 0, 1 and 2. What will happen if you were to fold this signal? When you fold the signal, the elements will take different locations. So this element will come over here and the other one, and the 2 will come and occupy the minus 2 position and the other one will go the other. As far as the 0th element is concerned, it will stay in its present location only. So let us let us first write down the signal x of minus n, which is the folded version of the signal. So the signal is, so if you were to fold the signal, this will be 2, this is 3, then minus 1 remains in its place, 1 goes here and this is 2. Okay, so you can see the origin is over here. So our formula for determining the even component is x of n plus x of minus n. So these two are to be now added and then divided by 2. Now let us continue that over here. So I will write x of n over here, which is 2. Yeah, so I can write it over here only. X of n is 2, 1, minus 1, 3 and 2. If you add these two signals, you get 2 plus 2, 4, 3 plus 1, 4, minus 1 is minus 2, 3 plus 1 is 4 and 2 plus 2 is 4. And you can substitute the same in this relation here. Can write the value as 4, 4, minus 2, 4, 4. So the resultant even component is, this whole signal is to be divided by 2. So 4 by 2 is 2, again 4 by 2 is 2, then minus 2 by 2 is minus 1, then 2 and then further 2. So you can see that the signal that we have obtained, that is the even component, is having symmetry along the origin. So this is the way in which you can decompose a given signal in even and odd part. On the same lines, let us now try to obtain the odd component. In order to obtain the odd component, so I shall first remove this. The given signal is x of n. Okay, so let us write down x of n. Once again, the signal is 2, 1, -1, 3 and 2. Formula for the odd component is x naught of n is half into x of n minus x of minus n. Okay. So in that sense, I must be subtracting x of minus n from x of n. So what is 2 minus 2? Resultant is 0. Similarly, 1 minus 3 is minus 2. Minus 1 minus of minus 1 is 0. Similarly, 3 minus 1 is 2 and 2 minus 2 is 0. Okay. So the origin is here. And this is to be further multiplied by half, or you can say divided by 2. Therefore, the component, odd component x naught of n is 0, minus 1, 0, plus 1 and 0. This is the odd component. So even component and odd component can be obtained in this fashion. Let's take another example. Let the signal be x of n. Let the signal x of n be 3, 2, minus 1, 2, minus 4. This is the signal. In this case, let us assume the origin to be at 2 location. So if you were to mark the values here, so this is minus 1 position, this is 0th position, this is 1, this is 2 and the third. So there are totally 5 samples in this given signal. Our task is to obtain the even component and the odd component. So you now know that you need to obtain the time reversed signal. So when you reverse the time, in this case, the sample at location 1 will take up the sample at minus 1. The sample at location 2 will take up the position at minus 2 and 3 will go to minus 3. On the same line, sample value at minus 1 will occupy plus 1. So the whole signal will now be folded, or reversed signal will be, this is the signal. And where is the origin? So the origin is at location 2. So these two signals are now to be added. So addition, I want you to understand the addition of signal with respect to special attention to the position of the signal. So I would like to rewrite the signal over here, which is 3, 2, minus 1, 2 and minus 4. So this is the origin here. This is the origin. This is x of n. What you can see on the board is the x of n. And I am going to next write the x of minus n corresponding to the same value. So the origin value is over here. So origin of both the signal have been written coinciding with each other, and this is 3. What about the other 3 values? So minus 1 is here, 2 is over here and minus 4 is over here. Now the task is to add these 2 signals. Let us look at the possibilities. At location of 0, right? This is 0th value. This is 1, this is 2, location 2, and this is 3. Similarly, this is -1, this is -2, and this is -3. So what is this? This is n. This is the index value. So -3, -2, -1, 0, and so on. If you were to add these two signals, then 2 and 2 are to be added. So the resultant will be 4. Resultant is 4 over here. Similarly, at n equal to 1, if you were to see, there is -1, and then there is 3. So -1 plus 3 is 2. You can add. On the other side also, you can get the same value. But what about the values at n is equal to 2? At n equal to 2, the given signal x of n has a value of 2, whereas the folded version of the same signal is not having any particular value over there. So the idea is to consider that value as 0. So we are going to consider this value as 0 and then proceed with the addition. So 2 plus 0 is 2. Okay. On the same line, at location 3, the folded version doesn't have any value. So the resultant will be over there -4. -4 plus 0 is -4. Applying the same thought on the other side, we can substitute 0 here and 0 here. So this doesn't change the nature of this signal. Appending, this is called as appending zeros, and we can proceed with the addition. 0 plus 2 is 2 and 0 minus 4 is -4. So the origin is over here. Now if I were to observe the procedure that we have done till now is only the addition. This is to be now multiplied by half or divided by 2, one and the same. So when I do that operation, I can write it as 1 by 2 into this. Therefore, the even part, that is x even of n, the resultant is -2, 1, 1, 2, 1, 1 and -2. The nature of the even signal is that it is symmetrical with respect to the origin. You can see that the middle value is 2, and on either side of the origin you can see that the samples are same. So that satisfies the condition. The condition was that the even signal is 1, which is x of minus n is equal to x even of n. So this is the even signal. Now I would like to continue the same example by considering the odd component. So you know the formula for odd part, which is x naught of n is half into x of n minus x of minus n. That means the folded version is to be subtracted from the original signal x of n. So x of n minus x of minus n, and finally it needs to be divided by 2. So let's arrange the things over here. So the given signal is x of n. Given signal is x of n, and I am going to subtract x of minus n from x of n. So you already know the values of the samples like zeros over here. Why we have appended these zeros? So we can continue with the same. So 0 minus of -4 is +4. Similarly, 0 minus 2 is minus 2. 3 minus of minus 1. So I have to subtract minus 1 from 3. So minus 1. 3 minus of minus 1 is 4, because it is 3 plus 4. Similarly, I need to subtract 2 from 2. So this is 0. Similarly, you have to subtract 3 from minus 1. So this will be minus 4, and 0 from 2, and 0 from minus 4. So this is the value, and I am going to determine the half of all this. So this will be, that is the odd part, odd x naught of n will be 2, because 4 by 2, then minus 2 by 2 is minus 1, then 4 by 2, 0 by 2, minus 4 by 2, 2 by 2, and minus 4 by 2. This is the odd part, and you can, by looking at the signal itself, you can observe how the signal is odd. The reason is the origin is 0, then 2 and minus 2 are conjugate of each other. Similarly, minus 1 and plus 1 are opposite sign of each other. Similarly, 2 and minus 2 are also of opposite sign to each other. Okay, so this way you can determine the even component and odd component. One interesting thing is that if you add the even component with the odd component, we must obtain the signal x of n. So that can be used as a check for your answer. Quickly you can add the two signals, and then you can determine the total signal x of n. So if you get the x of n, then your method is, and your steps are correct. Look at the signal x naught of n. X naught of n, if you observe, the zeroth signal, that is the sample at location 0 is 0, and if you were to add the samples at minus 1 and plus 1, it will again result in 0, because 1 is the magnitude wise both of them are same, but sign wise they are opposite. So if you have 2 here, you will have minus 2, and you can see the samples at minus 2 and plus 2, the both magnitude values are 1, but one is plus 1, the other one is minus 1. So if you add plus 1 with minus 1, again you get 0. So the nature of an odd signal is that if you were to add all the samples of the signal x of n, odd, all the samples, then it will be resulting in 0. So let us try to prove this concept. Let us assume the signal, a given signal is odd. Let us consider the summation of x of n, and n is equal to minus infinity to plus infinity. This summation can be divided in 3 parts. The first summation, I will consider x of n from n is equal to minus infinity to minus 1. Then I will consider one value at x of 0. Then I will consider one more summation at x of n, where n is ranging from 1 to infinity. So if you were to look at the summation from n is equal to minus infinity to plus infinity, that same thing has been divided in these 3 different sections. So total on the right hand side is the summation from n is equal to minus infinity to plus infinity. Now let us make a small rearrangement of the signal over there. So if I were to, since this is summation, I can write it as x of n, okay, n, and n is equal to minus 1 to infinity. and this is x of 0. I just changed the order of summation. Okay, so this is 1 to infinity x of n. So in both the cases you are going to get n is equal to 1 to infinity, and the last term is n is equal to minus 1 to infinity. Here let us make a small readjustment with the numbers. Okay, sorry, this is minus infinity here. Yeah. So instead of having n is equal to minus infinity to plus infinity, let us have the negative term being reflected with n. So I can consider this as n is equal to 1 to infinity itself, but here I shall have minus n. Instead of having plus n, I will have minus n. So n at n is equal to 1, this is x of minus 1. So the meaning is not changed, but the terminologies are suitable for our further operation. So I shall have x of 0 here, and I am not going to change the last term here. This will be as it is, x of n. So n is equal to 1 to infinity. Now, just now we had discussed that the signal is odd. The signal being odd means that you have this possibility of x of minus n being equal to x minus x of n. Okay, so what I can do is I can replace this whole thing by minus x of n. Okay, so this whole part I'll replace it as minus x of n. Reason is that the signal is odd, and the definition of odd signal is that x of minus n is same as minus x of n. This is the definition. So based on that definition, I can also observe that the negative sign is over here, which can be brought out. So you can write it as minus over here. So this leads to the cancelling of the first term over here with the last term. So the remnant is now only the signal x of n, which is equal to x of 0. And if you can look at the previous example over here, what is the signal? What is the signal value at n is equal to 0? At n is equal to 0, you can see that the signal value is 0. So for an odd signal, x of 0 is 0. So it proves our hypothesis over there that sum of all the samples of a odd signal will be equal to 0. Let us continue our discussion with the periodic and non-periodic signal classification. Till this lecture, we have seen the classification as continuous time and discrete time signals, even and odd signals, and the decomposition. In this lecture, let's continue the topic on the periodic and the non-periodic signals.